So now that we've covered all four of the cases that we're going to be considering here in our calculus class, I wanted to take a step back, right, and just kind of summarize the four different techniques that we've developed. Okay, so if you have a linear factor, then that becomes a over that factor, a constant, right? If you have a repeated linear factor, then the linear factor appears once for each degree. So for example, I would have b over x minus 2 plus c over x minus 2 squared. And if we have a quadratic factor, that gets replaced with a linear factor. So you notice the trend here, right? The factor that I put in the numerator is always one less than the degree of the one I had in the denominator. So here I would use dx plus e over that factor. And if we have repeated quadratic factors, well, we combine the two methods here. I would do fx plus g over x squared plus x plus 1 plus hx plus, okay, you really don't want to use I because it looks too much like a 1. So I would skip and do j here over x squared plus x plus 1 squared. And those are all the cases we're going to consider. I've said that before in these lectures. However, if for some strange reason you find yourself in a situation where you have to do something that does have a factor with a bigger degree in the denominator, you just extend this in an obvious way, right? Because like I pointed out a second ago, the polynomial in the numerator is always 1 degree less than the one in the denominator. So if I had to do something with this cubic, irreducible cubic, then I would put kx squared plus lx plus m. You just kind of can extend this process in a very natural way. Okay, now obviously I'm not actually going to try to do this, right? And find the decomposition of this thing. We're already up to m. I don't even know 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 variables. I don't think so, right? But this is right. Just a quick summary of all of the methods that we've talked about so far. So you kind of got them all in one place. Okay, so before we start moving back in the direction of calculus, an obvious question to ask is, well, when should I use this method? And are there situations where I shouldn't use this method? Okay, well, this method is a good choice when the denominator can be factored, and when you have two or more factors in the denominator. So I would not use this, for example, for something like 1 over x squared plus 1. It has a single polynomial in the denominator, and it can't be factored. That would be a poor candidate for this method. And you're also only going to use this when the degree of the numerator is less than the degree of the denominator. Right? So again, for example, I would not use this for something like x cubed plus x squared plus 1 over x minus 2. Right? There are other techniques that we can use for both of these, and we're going to talk about that. One more lecture to go first. Right? We're going to talk about all of these situations when we get back to actually trying to apply this stuff to calculus problems. So we do have one more thing to talk about before we can really get back into calculus, and it's that second case on the previous slide where the degree of the numerator is greater than the degree of the denominator. Right? In that situation, what we're going to do is we're going to fall back on polynomial long division. We're literally going to divide the expression out, right? And it's going to give us a polynomial plus a remainder, and that remainder will be a rational function, right? And of course, the polynomial part is easy to integrate, and then we're left to kind of take a look at that rational part and see what we can make of it.